Hello, my AP students. We'll be talking about gravitation, conceptually, mathematically, and density. By gravitation, I'm referring to gravity fields. In another closed video, we'll talk about gravitational force, but it's the same major ideas. So once again, we're talking about gravity fields, density, and the ideas involved. So first, let's talk about the concept of a gravitational field. We discussed the idea of space-time as a flat surface, and how it bends when you put mass in. So that mass bends space-time around it. And that bend of space-time we can model as gravity. And remember, this idea represents the field due to gravity and a field interaction between two objects. We also said like ripples in a pond, this field travels or propagates at the speed of light, which we call c. And this is just a model. It's not exactly how reality works, just ways of interpreting it. As you can see right here, our picture has got one mass, so this is the field, it does not involve a force. But we know in the back of our heads that fields create or fields cause forces. This is really important. So let's say we have two objects, object A and object B. Object A is really big, object B is really tiny in terms of mass. Object A makes a really strong field around it, whereas object B makes a very weak field around it. And also remember, these fields decrease in value as you get further and further away from them. It's a 1 over r squared relationship. So object A is an object B's field, but A really strongly interacts with B's weak field. B, which is tiny, weakly interacts with A's very strong field. So they both make a force, but those forces are equal. A strong interaction with a weak field can yield the same force as a weak interaction with a strong field, and that's where Newton's third law comes in. So let's talk about these gravitational fields. The first thing you should know about them is they have a direction. And for these, it's really simple. The direction is always towards the object making it. So the Earth's gravitational field is always pointed towards Earth. Your gravitational field is pointed towards pointed towards you, I'm sorry. So the sun's gravitational field is that way. And also remember that the closer you are, the stronger the field. And these fields are created by a single object, but they're felt by every other object out there. So you feel the field of everything around you, and you make a field that everything else feels. And the mathematical relationship is little g is big G m over r squared, or d squared if you want to call it that as well, where little g is the field strength, which we call an acceleration. Remember, acceleration is just the strength of the field. Big G is the gravitational constant of the universe, 6.67 times 10 to the minus 11. Doesn't matter where you are for this. It also doesn't matter what speed you're going at for now. M is the mass making the field. So it would be the object making it, not the object experiencing it. And r is the distance you're looking at. So it's the distance from the object's center of mass to the point. So those 3 points I've labeled, they all have different field strengths because they're different distances from the sun. So for example, Earth, as Will Smith likes to say, it's not exactly perfectly straight, or perfectly round I should say. So the higher you are from Earth, the less gravity is, because you're closer or further from the center mass of the Earth. So the closer you are, the more gravity you have, more gravitational field there is. Now, for example, if you were to put in the Earth's mass for m, and the average distance from the center of mass of the Earth to the crust where we are, m Earth in kilograms, and the radius, or from the distance from the center of mass to where we are, in meters squared, and multiply 6.67 times 10 to the 11, you get 9.81. And that's the acceleration due to gravity. The higher up you are, that r value goes up and gravity goes down. So now let's talk about something kind of different. Gravitational mass versus inertial mass. These are key ideas for the AP exam. There may be 1 or 2 questions about them. These are 2 different ways to describe how much mass something has. And it's kind of like they're 2 different tests to discover the mass. My cat agrees. You're right, Victoria. There are 2 different ways. Gravitational mass is like how much the object interacts or relates to a gravitational field. So you have a field, you put this mass in, and it's how much it interacts with it. Inertial mass is kind of like how an object accelerates or reacts to a net force or an imbalance. My cat's being really loud. I don't think she likes this different discussion. Because in physics, in every experiment we've done, these 2 values have always been the same. So it's kind of like the mass you get from relating to gravity and the mass you get from relating to net force should always be the same mass. So for example, let's say we're going to test 2 different cats and figure out how their masses compare. So I have 2 cats, Victoria and Ellie, and you're definitely hearing Victoria right now. And let me give you a hint. She's the biggest one too. So we're going to test these 2 cats, A and B. A test, for example, using gravitational mass is you put them on a scale that uses gravity. Or you put them on a spring, and whichever one compresses more, which is X value, is heavier. So if B pressed more down, for both cases, B has more gravitational mass. And then an example of inertial mass was you pull each with the same amount of force. Let's say 10 newtons. The one that accelerates more has less mass. Or if you use F equals ma, you can calculate the mass that way. But both masses should be the same. So in physics, sometimes you talk about using gravitational mass to find something using gravity, or you talk about inertial mass. Gravitational mass is easy to do on gravity, on a planet. Inertial mass is able to do anywhere. You may hear the phrase inertial frame of reference in the future coming up soon. So now we're going to do kind of an example with density. We're going to find where we need to start doing some major league thinking. Now, density is mass over volume from chemistry. That little rho on the left is the Greek letter rho. It stands for the density of something. Mass over volume. So here's an example of how our thinking may go wrong. Let's say we're talking about Earth. And Earth has some mass, which we know. We're not going to give it to you numerically. It's just a mass. And it's got some radius. RE and ME. Let's say there's a planet that is just like Earth. Same composition, but has twice our radius. What would the value of gravity on the surface of the planet be? Now here's where kind of regular logic comes in and it's wrong. Your first thoughts as a student, okay, the mass that we're looking at doesn't change. It's just like Earth's got to have the same mass. And the radius is now doubling. Mathematically, gm over r squared, I put me and re for the Earth. If we double that radius, that's a doubling radius squared, I'm going to get, you see about here, I put the full R in front because it's 2r times 2r. I'm going to get 1/4 the original gm over r squared of Earth, so I should only get 1/4 the value of gravity. But that is completely wrong. The logical assumption that was wrong about this is that if Earth doubled in radius and it's the exact same composition, the mass must change as well. A way to think about it is, if the planet's got the same density as Earth, if it's a lot bigger, it has to have more mass to compensate. we have to find how much the mass changed by. So we know that the radius doubled. The question is, how much will the mass of the planet be compared to before? I'm going to use the idea of density of Earth. And density is mass over volume. Now, if you double the radius, does the volume double? And the idea is, no way. We're going to find out how much the mass changed by. We've got to find the volume change first. I know the volume of a sphere, which Earth is, pretty much, is 4/3 pi r cubed. Now, all I care about is the r cubed value, because that's the only thing that's changing. The 4/3 pi is just a constant. So by doubling the Earth's radius, it's kind of like I'm changing the volume by a factor of cubed. So I'm cubing the double, which is 8 times as big. So if you double the radius cubed gets you 8 times as much volume. And if it has the same composition as Earth, if you have 8 times the volume, you must have 8 times the mass. So a planet that's twice the radius of Earth is 8 times more voluminous, and if it's got the same density, it means it has 8 times more mass. So back to my original statement, and I'm going to say, yeah, the radius doubles, but the mass is now 8 times as big as before. I want to find the gravity value. Big G m over r squared. Big G doesn't change, because it's a constant. The mass not doubles, it's 8 times, so I'm going to rewrite that. And the radius is double, and it's squared. And you can see the gravitational constant will be 2 times big G m over r squared, which is the original value. Or to summarize it, you get twice as much gravitational field and the surface as Earth's is, which would be twice as big, which would be 20 meters per second squared. And that helps explain some of the physics we're going through.